Sometimes. Yeah. And I'll tell you that means it's still bad. Oh man. Okay, so I'm sure you were wondering this along with everything else you were wondering. You're thinking, last year in pre-calculus, we were doing like a lot with composite functions, like f of g of x, g of f of x. So like you had to put a function within another function. You would like check for inverses. And I'm sure at some point in the last couple of weeks you thought, I wonder if we're ever going to have to derive those. We get to learn how today. So 2.4, it has the rule is called chain rule, and it's going to be about composites. Before I actually show you the rule though, we're going to just kind of get more familiar thinking back to composites and that kind of thing. And we're going to make some little rows, I'll say, little columns. And we're going to have 4 columns. We're going to have non-composites, composites, inner, and outer. So just a little, so this is your f of g of x and your g of f of x. The whole idea behind those is one function is plugged into the other function. That's the basic idea. So just to kind of wrap our mind around that, if we had a function y equals x squared plus 1, there is nothing about that where something else was plugged into it. Those are just very standard monomials that have been added together to make a polynomial. Just a pretty easy function. But if I tweak that just a little bit, this now is a composite. There's like more going on than just polynomials. We have multiple math operations going on. Now, in order for us to be able to do the calculus well, we need to be able to pick out what the innermost function is and what the outermost function is. So just like when you did f of g of x was the inner function, the f of was the outer. So a lot of times your inner function is going to be the part that's just within something else. Makes sense, right? So for our inner part, it's just the x squared plus 1. That is within the square root. The outer part is the square root. But we don't want to put an x here because x is already being used for the inner part. So one thing you'll see, and we'll come back to using this a lot this year, we're going to put the square root of u. We're going to use another variable to represent what that outer function is, and u is the common one to use. So there's kind of a breakdown. Now let me give you another one. Let's say we go with our standard trig function of sine of x. Just your basic sinusoidal graph. Nothing composite about that yet. But if I tweak it to look like this, now there's more going on to that. In essence, it's a transformation, and that is a form of a composite. Okay, now if you think about this, isn't another way we could write this that would be appropriate? We could do that. And kind of what that does, if you see parentheses, that kind of sometimes helps you see what the inner part is. So the innermost function for this is 6x, which means the outermost part is the sign, but we gotta put a u there as our placeholder. And for trig, you always have to have trig of something. If you just have SIN, that just are 3 letters that don't have anything to do with math. So you always have to have it of something. And so we'll do sign of u. All right, let's break down another one. Let's do y equals 3x plus 5. So just a basic binomial. But then if I take this, it now becomes a composite. And then our inner part, easier to see with those parentheses, 3x plus 5. And our outer part is to the 5th power, so we'll put u to the 5th. Okay, let's do one more with trig, and then we'll get to the actual rule. Let's say we have y equals the cosine of x, basic, non-composite. And then if I change it to this, it now becomes a composite. But remember the way that they square things is weird. So technically, remember, when you have that notation, it's technically this. And again, the parentheses sometimes help us pick out the innermost. So here, the innermost part is the trig, and the outermost part is the power. Okay, so there's our little review of composites. Now let's get the actual calculus rule. So we'll put our little notation up here, the derivative of a composite. So the derivative of f of g of x and then here is what it actually looks like. F prime of g of x times g prime of x. Okay, now I've got a saying for you on this one too. So you can, if you like the formula, you can use the formula. I've got a saying, and here's what the saying is. Take the derivative of the outer keeping the inner times the derivative of the inner. And that inner and outer part comes just from what we're going to find like we did in the chart above. And so we'll be finding all of those as we go to derive our composites. Are you ready to see one in action? Okay, we'll start off just nice and easy. And the first one we're going to look at, we're going to find the derivative of y equals x squared plus 1, all being cubed. So one of the things that might be helpful as we're learning this and we're just kind of getting going is if you off to the side want to identify your inner and outer with the I and the O, it might kind of help organize it in your brain. And so if we look at this x squared plus 1 cubed, any guesses on what the inner is going to be? Yeah, x squared plus 1. And then what's our outer going to be? u cubed. Okay, so now to kind of follow our rule, we want to derive that outer part first. So if you just think about u cubed, pretty standard easy power rule. If we were going to derive u cubed, it would be 3u squared. But we don't want to keep u in our answer because that's like a construct that we kind of entered into the problem. So you derive this 3u squared, but you still keep the inner part in there. But don't change the inner yet. So derive the outer, keep the inner the same, times the derivative of the inner. So we derive this part right here, 2x. There's our derivative. And so then just like everything else, if I said, hey, what's the slope at 1 or what's the slope at 100, we would just plug that in to our derivative and we would know at that moment what our slope is. But this is our answer for a composite. Not too horrible, right? Huh? Yeah. It would be equivalent. It wouldn't, you could like get them to work, like you could get them to match, but it would be equivalent, yeah. And you could do a triple product rule. It's Mr. Short over there. Oh, he wanted to hear about chain rule. I don't know. All right, let's try another one. Any other questions right now? Okay, let's try this next one. Actually, yeah, we'll try this one. Let's go with this. Okay, now there's a couple things going on. Do you see how there is a quotient going on right there? Do you see the part that's composite in the denominator? So technically, we've got a couple rules going on. But I'm going to show you how you can make this just one rule. So you know how we've talked about that trick of bumping things up? We're going to bump this part in the denominator up, and we're going to make it look like this. So mathematically, that's okay to do. Bump it up, use your negative exponent, and now there's no longer a quotient. Now it's just a composite. And when we think about this composite, the inner part's pretty easy to pick out. It's the part with the parentheses, so 2t minus 3. The outer is like everything else, so it will be negative 7 u to the negative 2. So we could, but then we'd still have to do quotient. So I'm trying to make it so we don't have to do two rules. So this kind of goes with Toby's question though. There's always like kind of multiple ways you can solve something. So we could do that. We could do negative 7 over u squared. We just then have to do low d high minus high d low as well. Other questions right here? Okay, now let's try this new chain rule out. I'm going to make it a dy dx. Throw that symbol in there. Okay, if we were just deriving negative 7 u to the negative second, what would that derivative be? 14u to the negative third. So we'll keep the 14, but in place of the u, we'll put the inside, and then to the negative third power. So there's our derivative of the outer, keeping the inner, and then we need to multiply by the derivative of the inner. And this is where it gets its name. Chain rule, you're like chaining on the derivative of the inner, multiplying it on. Not that it's a great reason for a name, but that's where it came from. And then just like before, we have to fix negative exponents. So that part with the negative third power will bump down, which would leave 14 and 2 on the top. I'll make that a 28. And there's our derivative. Questions there? Okay, let's try another one. Next one we're going to look at is going to be a trig one. Okay, so let's do y equals the sine of 2x. Okay, so we had one kind of like this in that chart to begin with. The inner part, if you think where would we put parentheses, it would be around the 2x. And so that means our outer part is the sine of u. So when we go to derive, take the derivative of the outer. So the derivative of sine is cosine. Keep the inner times the derivative of the inner. And there would be our answer. All right, let me give you one to try. Give you a chance to work this one out. Y equals, let's go, 3x minus 2x squared cubed. Try that one out. And then one thing to check, make sure for that derivative of the inner that you're chaining on, just make sure you have parentheses there, or else it'll be saying it wrong because we're multiplying by the whole derivative of the inner. Pretty nice, huh? All right, I think we should go back to do some trig ones because sometimes trig can get a little tricky. So let's try this one next. Let's go y equals, let's throw a secant in here. Secant of 15x. So here again, if you think where the parentheses would be, the inner is your 15x. The outer is secant of u. Okay, so I hear the papers flipping back to what is the derivative of secant? Secant tangent. So when we derive the outer, it's going to be secant tangent. Now again, trig has to be of something, and we're supposed to keep the inner. So we need to put a 15x with both of them. Because technically the derivative of secant x is secant x tangent x. But now we're keeping our inner, so make sure we put that 15x with both of them. And then times the derivative of the inner, which is 15. So there's our derivative there. Okay, let's try another trig one. Let's do y equals the square root of the cosine of x. Here, the trig is the inner part. So the inner part is the cosine of x. The outer part is the 1/2 power. I'm going to write that as u to the 1/2. Okay, now we're ready to derive. So if we derive u to the 1/2, we're bringing 1/2 down, but keep the inner and subtract 1 from the power. So that's our derivative of the outer, keeping the inner, times the derivative of the inner. And then because we have that negative exponent, we do need to fix that. So this cosine part will join the 2. So we could make this then look like this. And again, if you want, you can leave it as a radical, or you could make that a square root. And then also, you don't see this often, but it follows the rules. Could look like that, but you really don't see that often. They don't usually write it like that. And that would be our derivative. Okay, I'm going to show you my favorite chain rule for trig next. Okay, so as we write that down, our goal is to kind of think of inner and outer, and you're kind of thinking about where the parentheses would be. Any ideas? Sine 4x is correct. 2 parentheses is correct. This one has multiple inner outers. That's not the right reaction. Emily looks at it and she goes, multiple. Okay, so we have to have the correct order. So first of all, I'm going to rewrite it with my parentheses. So this is the sine of 4x with parentheses, all being cubed. So we have to think big scale first. Big scale, this is our inner thing. This is our outer thing. So what I'm going to do with my inner and outer is write it like this. My inner is going to be the sine of 4x. My outer is going to be u cubed. But then this has its own. So I'll have this little, it's almost like a tree diagram, little branch. For the sine of 4x, my inner is 4x. My outer is the sine of u. Also, another reason it's chain rule, you can chain on multiple things, which is what we're doing. Okay, so as we go to derive this, y prime. So we look at the green part first. The derivative of the outer is 3u squared. Keep that first inner. So the derivative of the outer, keep the inner, times the derivative of the inner. So now when we go to derive this, we have a brand new chain rule. The derivative of the outer, cosine, keep the inner, times the derivative of the inner. That's it. I love multiple chain rules. Now, if we wanted to write it like so you could see it in a different form, just to kind of start seeing how they write trig, they would probably, like if this was a multiple choice question, this is probably how you would see it. They would fix that squared on the sign and join it. But again, right now, this line is fine. We can still do math with that line. Questions on our first multiple one. I love these. It's almost on the same level when you have difference of squares that you get to do multiple times. Those are always fun. Okay, now, next one that we're going to do, we're going to practice complete simplification because they're going to ask us another parts of this question. So here is what the example is going to say for us. We are going to find the points where f of x equals the cube root of x squared minus 1 squared has a derivative that equals 0 and where the derivative does not exist. And here we're starting to get into like further process. So just be a little bit more beyond just deriving it. And so we want to know the spots where this derivative equals 0 and does not exist. And again, those are usually important because when people use derivatives, the points where it equals 0 and does not exist are usually key factors in that graph. Where something equals 0, behavior is changing. Where the derivative doesn't exist, maybe something big is going on. So that's why they ask us a lot about 0 and does not exist. But before we worry about that, in order to answer it, we just need the derivative. So we're going to start by deriving this. We've got a lot going on with that derivative, but I can make that one chain rule, not multiple parts. I can rewrite the original as x squared minus 1 to the 2/3 power, and it means exactly the same thing. And then, once I have that, I just have one inner and outer. My inner is x squared minus 1. My outer is u to the 2/3. And then we'll derive. So f prime of x, take the derivative of the outer, 2/3, keep the inner to the negative 1/3, times the derivative of the inner, so times 2x. Okay, now as we see that, we're going to fix the negative exponent. So the part with the parentheses, we're going to bump down to be with the 3. The things that are left on top are 2 and 2x. So I'll make that 4x, and then on the bottom, 3 times x squared minus 1 to the 1/3. And this is our derivative. Now, if we were asked for derivative, we'd stop there. But now they're asking us for some times what happens with this derivative. Okay, so let's go back to nice old algebra 1. If you had the fraction 0/7, what does that equal? If you had 0/11, what does that equal? Also 0, okay? Good, good. Good algebra 1 question. Okay, now what if you had 17/0? 19/0? Okay, you guys pass algebra 1. Now, what that means is if we set the top of this equal to 0 and we figure out where it equals 0, that's where the derivative equals 0. If we set the bottom equal to 0, that's where it's going to be undefined. So you're going to hear me say this a ton over the next chapter. When you're asked to go farther than just finding the derivative, always make it one fraction. And if you make it one fraction, then you set the top and the bottom equal to 0, you're going to find the stuff that you need. So remember that. I'll say it until you're sick of it, but one fraction is going to be key for when we have to do further things. So when we set the top equal to 0, 4x equals 0, divide by 4, we get x equals 0. Then when we set the bottom equal to 0, first we would divide by 3, still 0. Then to get rid of the 1/3, you would cube each side, still 0. Add 1 to each side, so now we're at x squared equals 1. Then square root each side, and we get x equals plus or minus 1. And then just to kind of describe what's happening with each of them, the x equals 0 is where f prime of x equals 0, and this plus or minus 1 is where f prime of x does not exist. So that means something significant is going on, and we're going to be taking the next chapter and a half figuring out those significant things. But those are key spots on the graph. So that's starting to get into simplified. Feeling okay? Okay. Next, what I want to show you is this question. We're just going to go back to another derive question. Just simply derive this. Okay, we got parentheses in there. So is it pretty easy for us to pick out our inner and our outer? We've got that inner part with the 3x minus 1 and the x squared plus 3. Our outer part is being squared. What's going to make this fun about the inner part? We get to do a quotient rule when we go to derive the inner part. So now this one, we can't get rid of quotient. We can't bump that up. I mean, technically we could bump it up, but that would create a product rule and another chain rule. So we're going to have, this is our first one where we're going to do multiple rules. And so one of the things when we start to get multiple rules involved, you have to think which one's the biggest rule. So chain rule applies to this all. Quotient rule only is going to be part of it. So chain rule is going to be our overarching rule. So we've got the inner is this whole fraction. The outer is u squared. All right, let's try this out. Derivative time. So we derive the u squared part. So we bring the 2 down, keep the inner, and then it will be just to the first power. Times the derivative of the inner. So now when we go to derive this, we're back to low d high minus high d low over low low. So low d high minus high d low over low low. And we can leave it like that for now. That's our derivative. How are we feeling about chain rule overall? Okay, think we're going to stop there for today. I think that's a good spot to stop. So we will continue. There's just a couple other things we'll do with this Monday, and then we'll get ready for our quiz.